So we are looking at this C program implementation with the Yaxim of the MM1 system, right. So we talked about the different components, the arrival process, right, which captured how packets are generated and queued, and actually the service process is hidden. We used the resource which is available in Yaxim to do that. So we could also have done that separately. We could have written our own code for adding a packet to a queue, dequeuing that packet, all that could have been done by ourselves, but for the sake of convenience we are using that resource that is available, right. We look at another example where we do the dequeuing ourselves, okay. In this example we are simply just using the resource thing. So so questions?
If I want to know the queue length at each instant of time, then how can I do that?
Okay. So the question is, how do we find out the queue length of the system at intermediate points in time, right. In this case I am only printing the queue length at the end of the simulation. So this, if you look at the statrec report function, this takes as an argument a qstat pointer function, which in turn returns a stat record, and this stat record is continuously updated by the simulator, by Yaxim. So we can call this at any point in time to look at the current length of the queue. So you can print not only just the mean, right, you can print other things also, you can print the range of values that you are looking at. So there is a fairly sophisticated set of functions that are available as part of the statrec to get all other values, right. So we can look at the mean length of the queue at different points in time, right. So that is what here I am looking at the mean length of the queue at the end of the simulation, right, based on all the samples that have been collected by the system. So in terms of sample collection for mean length, customer delay is very clear, because every time a packet finishes I compute I just update the statistics record, whereas mean length is not like that, right, because the length of the queue can be measured at any point in time, but you look at some specified instance of time and you can measure the length of the queue at that time. Or you can also measure the length of the queue only at packet arrivals or packet departures. You can define as to when you want to do these measurements and then update the samples accordingly, right, and we can get it correspondingly. So that is the basic notion of that's the basic idea here, right. So there is an arrival process which we discussed earlier on, and then there is the customer which is also discussed earlier on. So these are the two, one is the event handler customer and the other is the process logic, right. And if you look at it, typically all the process logic functions will be like this, would be mostly endless loop that keep on generating packets, and then when the system terminates automatically everything gets cleaned up, okay. So that is what we have so far. Now let us try to run this code and see if actually we are able to match some of these things, right. So I said that we have this MM1 queue minus h, right, and the different parameters were arrival rate 0.5, departure rate 1.0, and we said we do not want replications, right. I am not doing that converged, I am just giving it some raw value. So let us say I will run this for 100 units of time, okay. So now let us look at what the output of the system is. Okay, there is a whole bunch of values that have passed by, let us look at this slowly, okay. So first we printed the length, right, and so the number of samples taken so far, actually this is the mean length, let us look at so the mean length of the queue is 0.444294, that is something that Yaxim has measured for us, and the mean utilization of the system is 0.354596, this is the mean utilization of the server, okay. Now we have to look at these two numbers and say, does this relate to what we know, right, is what is utilization defined as in MM1 queue? Ratio of arrival rate to departure rate, right, lambda by mu. So lambda is here is 0.5, mu is 1.0, but the mean reported by the statistic server utilization is only 0.354596. So what is wrong there? I should be getting 0.5, right, 0.5 should be my row value, utilization value, I am only getting 0.35. So why would that be? Because I have not run the simulation long enough, it is only 100 units of time, okay. Number of samples collected is very small. Now how many samples do you think would have been collected in terms of customer completions? For this given set of parameters, how many customers would have completed service? Approximately, it is arrival rate 0.5 into, this is what, number of arrivals per unit time, this is the time that we have studied the simulation, run the simulation for, therefore should be about 50 packets, right, 50 customers should have been. So this stat record delay per customer, this is what we update every time a customer has finished service, right. So hopefully that will be around 50, number of samples is only 40, again why is it not 50? because this is number of things. This is again, remember that this is not a uniform process, it is a random, this is an exponential process, right, for inter arrival time. Therefore, if you look at only 100 units of time, it is not likely, you will likely not see 50 samples, right, only over very long periods of time will you be able to see that the number of customers equals exactly 0.5 into the simulation time units that you have run. Okay. Now let us look at finally this important result, right. So from simulation I am finding that the average customer delay is 1.09, okay, whereas theory tells me it is 2. We remember, right, theory says 1 over mu minus lambda is the average delay for MM1 system. So that is 1 over 1 minus 0.5, therefore 1 over 0.5 equals 2, but the customer delay from simulation is only 1.09. So clearly simulation has not been run long enough. Okay. Now for every system it is not possible to get a theoretical value. So what we do is we try to get some approximate values that lets us know whether our values are correct or not. That is why when you write simulations, right, you always have to know what is some close of expected value. Why is delay 34 milliseconds? Why is it not 100 milliseconds? How do you know that the numbers are correct? That is an important question that you have to ask before we publish the results, right. In this case, thankfully there is something we can compare. So what we see is that the number of customers from simulation is 0.44, whereas E of n, right, E of n is also from theory it is 1, right. Remember, E of n is lambda into E of t, so lambda is 0.5, E of t is 2, therefore number of customers should be 1, and that is also, or rho by 1 minus rho, whichever we want to look at it, right. So therefore this is clearly not adequate. So now let us run this for 10,000 units of time and let us see what the results are. So 10,000 unit of time, how many samples were recorded now? About 5,000 customers, right, have completed service. That kind of that is as unexpected, right. So we know that our simulation is kind of okay, is kind of correct, right, because you can never know whether the simulation is correct or not. Always there might be bugs in the system, somewhere you make a mistake. This is a way of validating your simulation. This is very, very important, right. Many people tend to forget that. You write an NS2 TCL script, run it, get the values and print it out and just keep going without really checking whether the numbers actually make sense or not. Okay. So then look at the delay per customer, right. Delay per customer is quite varying. The mean is what, 2, right, but look at the max value, it is 15 in some cases. It's very long time has been sent. In some cases it is very, very small, right, 0.00011, which means because it is exponential departure time, this packet had very small service time and there was no other packet in the queue. That is why this is, right, quite small, 0.00011 and so on. Okay. And so that is, so the standard deviation is about 2.12. So mean is 2 and the standard deviation is 2. Does it make sense? What is the standard deviation for delay? Is it also 2? Do you remember the distribution for average packet total delay in the system? What is the distribution? You should go back and look at Jain's book, right. So delay, mean packet delay is 1 over mu minus lambda, and it is also exponentially distributed. The packet delay is exponentially distributed with parameter 1 over mu minus lambda. Okay. And then if you look at it in the case of an exponential variable, is mean and standard deviation equal? In the case of Poisson, right, what is VMR equal to 1? In the case of Poisson, variance and mean are equal, right. In the case of exponential, standard deviation should equal mean. Again, this is a reminder for you to go back and look at the textbook and make sure that these values are indeed correct. Okay. So now we have run it for 10,000 time units. Now we are going to get, right, run it for say, I don't know, 10 million or 1 million time units. Okay. Now it might take a little bit longer to finish, but it finished pretty quickly. Now what do we see? Right. So delay from simulation is 2 and from theory is 2.00. We are now perfectly matching, right, and again we are able to get a million samples, right, sorry 500,000 samples, which is as expected. So therefore for this particular scenario this was adequate, right, we got enough samples and therefore we are finding that there is a good correlation between what theory tells us and what the simulation tells us. So I think whatever we have done is probably most likely correct in this system. And so this value for 100,000, so what people do is, now can I use the same value of 100,000 even if my lambda is this small? Now if I change my lambda to a small value, right, and run it for 100,000, this is 1 million time units, which will, how long will it take compared to lambda equals 0.5 and 1 million time units? and lambda equals this 0.00005 in 1 million time units. In terms of simulation runtime, right, which will be faster, which will finish sooner? The lower delay one. Why? Because the number of events generated is very small, right. Remember that the time for a discrete event simulation to run is not really proportional to the time, that max time value that you are setting, it is proportional to the number of events that are being generated. So when I set my lambda value very low, which means that the number of events, the number of packets generated is very small, right, and we will try to see what happens there. So how many packets are generated? Only 42 packets are generated, right, because that's the right, and therefore the number of packets are very small, therefore the number of events to be handled is also very small. Execution time of the code will be very small in that case, right. But now is this what do we see now, right? Average customer daily from simulation is 0.92, number of customers from simulation is 0.0, is very small, right, because the length of the queue is very negligible, right. Mean is 3.85 into 10 to the power minus 5, that is what showing up as 0 here, but it is actually a negligible value, but that is what you will expect, right. If your lambda is so small, then what will be the mean, right, it will be rho by 1 minus rho, it will be very small, right, it will be close to 0 almost, because rho is close to 0 in this case, right, it will be close to 0 by 1, and therefore it is going to be close to 0, okay. So that is the way that you, so now this is just the right basics of the system. So we have now, what we have not done is I have not turned on all the other options in terms of right, debugging and things like that, right. Debugging, tracing is non-trivial in such an environment because of the multiple processes, there is a lot of parallel processing involved here, and when you involve process synchronization, it is going to be even harder to deal with, okay. So that is our basic system now, okay. So questions on this? No questions, okay. So now let us look at the code and see where one could make changes. So I would suggest, right, that you modify some of these things, for example, right. So we said that I can replace the arrival process. So how, if I want to replace the arrival process with something else, what will I do? Where will I change that? Where will I change the arrival process? So this delay, right, I can play with the inter arrival time, I can replace this process with some other process, I can say random between 0 and say 50, or if I want to make it uniform, I simply use a constant value here. If I want to generate a packet every 10 units of time, I simply say generate every 10 units of time, right. This can be a constant value, this can be some random value. If you look at the axiom, there are other kinds of random functions also defined, you can use any of those particular distributions that you want. So this is very flexible, you can change the arrival process very simply. If I want to change the departure process, where will I change that? Instead of, if I want GG1, right, I can again replace this with any other function. All I want is a random number for the service time, and for service time exponential it is very clear, I have this predefined. If I want something else, I can even define my own distribution for the packet service time and pick from the distribution also, right. So therefore this is where I would go and change it, okay. So I can change the MM1 to GG1 system very quickly. Now how do I change this to MMM system? If I want to make this multiple server system, how will I do that? Where will I change that? Okay, let us go to user main somewhere here, okay, the answer is somewhere here. So new resource, this specifies one server, I change this to 5, I have 5 servers, and I want to change the scheduling discipline, I can change it here, right. I can make this round robin, then you can actually look at what the service, right. So you can change it to GGM, whatever that you want to, so that is very flexible, we can change that there, okay. Now what about we look at MM1B, right, we have, this is an MM1 system, right. Is this finite queue or infinite queue? This is an infinite queue system, because we do not really specify, right, a packet arrives, it simply gets queued, but what if you want to simulate a finite buffer queue, then what will I have to do? So then you will have to go and write your own server. In this case I am using the system server, the axiom server, which is by default giving me infinite capacity. If I want to replace that with finite capacity, I have to go and make those changes there. So I can basically take this thing and essentially do an MMMB system quite easily, right, and that's flexible enough for us to. So you will find on the web, right, several programs that says just give me the parameters for lambda mu and I will give you what the values are, and most of the time either they use the theoretical values or they will just use a simulation like this to let you know, right. And the good thing about simulation is you can actually not just look at the mean values, right, you can actually plot, for every packet what is happening, right. You can plot the distribution of the packet delays, distribution of the arrival times, so you get a lot more wealth of information. You can dig deeper into system behavior with the help of a code like this. You can introduce variables all over the place, whereas in the case of analysis mathematical model you cannot have, you don't have anything else, right. Of course you have to derive everything by the hard way, but not everything can be derived, especially when it comes to a non-Markovian system, right. So that is the advantage of trying to use simulation, but it has to be, again, it is a very useful tool. It has to be used very carefully, and one should always suspect that there are bugs in the simulation, right. Never be overconfident of your simulation. Make sure that every value that you are getting is indeed validated, right. Enough samples are being generated. Otherwise, you might end up giving everything a million time units, and what we saw was 42 samples for million time units. That's clearly not adequate in terms of statistical significance. Okay. I have not tried that. I have not tried whether the new resource allows me this notion. So I have actually defined only something. Student sound varaliya. Oh, sorry, Adit. I have not tried that new resource, how to make that finite buffer. But it is easy. If you look at, we look at the next example, Aloha.c, where actually I use finite buffers, infinite buffers. So it's straightforward. Yeah, you can. Yeah, you write the one NQ DQ, and only thing is you have to write your own scheduling discipline also if those things are not available. Okay, so that is as far as MM1Q, which is our sort of generic, right, performance evaluation. Any system will try to do that. Then let's look at another program, that another protocol that we have seen in class, right. We saw this Aloha. We have done analysis of Aloha, right. There are two different ways of analysis that we have seen in class. So let's look at that. So we all know how the star Aloha program works, right, or the protocol works. The packet arrives in the middle of a slot. You simply have to wait until the beginning of the next slot, right. That's the difference between Aloha and star Aloha. So therefore now we have a notion of a slotted time, right. So there is things happen. The packet transmission will happen only at the beginning of a time slot. A packet can arrive any time, but you can only take it for service at the beginning of a time slot. So this is our definition for the Aloha protocol. So now I have to emulate. In class we saw different ways of doing that, right, the mn, and we derived some basic g equals g into minus g e to the power minus g, all those theoretical formulae we derived, but let us look at whether we can actually verify that with the help of this simple simulator. Okay. So now to model this Aloha simulator, we need to create our own definition of a node. I have to somehow emulate a channel also, right. So there are only two entities are there, one is a node, other is channel. And the node I can replicate as many as I want, 100 nodes, 500 nodes, 50 nodes, right. Once I create one basic node structure, node object, I can replicate that to the number extent that is needed, that is a node. And a channel also I have to somehow represent in this particular system. Okay. So now the important part of the system is how do you model channel, how do you model a channel in a star Aloha system. So we have talked about states, right. When we talked about Markov models, we talked about the different states a system can be in. So what are the different states that a channel can be in? In any system, in any communication channel, right, the channel can be in some few states, right. What are those possible states? Either it's busy or it's idle, right, that's all. Channel is idle or channel is busy, but within that busy we can also classify one level further by saying that there is collision busy, which means more than one user is sending, that means the packet is lost, or it is generic, or there is only one customer, there one user that is currently transmitting, right. So there are three states basically, where there is no collision but successful transmission is going on, or second where the collision that is going on, or third the channel itself is idle. So we have to essentially capture the state of the channel in a given slot, and this happens every slot. So if you look at the system behavior, we can just look at it at the beginning of every slot. At the beginning of a slot, it's either idle, or it is a successful slot, or it's a collision and therefore wasted slot. That is the channel aspect. Then again we look at from the node perspective, right. So what are the states that the node can be in? So what are the states that the node can be in? Remember we did one started Aloha ISI model that we saw. We modeled the different states, right, of this was the SICOM 92 paper, if you recollect, those who were in the class, right. So there was the different states, right. What are the different states? So either the user is idle, right, and therefore no packet to send, or the user is transmitting in a particular slot, or the user is in and the user need not listen is assumed that it is always on. In this case the user is in back off, right. So what you do is you try to in a given slot either idle because no packet to send, because that is the definition of Aloha, right, slot Aloha. Whenever there is a packet to send you will send it in the next slot first time, but if there is collision you back off. So if you go into back off state, that means you are not going to send the packet right away, but you have the random back off, right. So that is the definition, idle, or you are sending in a given channel, or you had a collision and therefore you are in a back off state. So these are the three basic states for a particular end user. So this is how you define your system. Now we have to essentially represent this with the help of your various data structures, okay. So the parameters is the number of nodes n and the arrival rate lambda, arrival rate per node. These are the only two things we need, right. Remember that is a load on the system, each user is generating say 0.1 packets per second, there are 10 users and therefore the load on the system is basically 10 into 0.1, so there is one. And whether we have infinite queue or finite queue, that is a very small change, right. We will see how we can do the finite queue business now, okay. I will so this is the sum of the basic global variables, total number of nodes is defaulted to 16, infinite buffer size is defaulting to false. I have an upper limit on the buffer size in case it is non-infinite, this is the B value that we have seen in MM1B. Packet length is again fixed to be some number 1024 whatever that is, okay. And the default lambda, this is the arrival rate, is this one. Then there is a notion of back off probability, right. So every node has a back off probability that it will keep updating, if you remember that right, exponential back off and things like that. So you will choose your next slot based on this back off probability. So if your back off probability say 0.1 and you have a packet to send, then with probability 0.1 you will resend the packet, otherwise with 0.9 you will back off and do it sit quietly, right. That is your back off probability definition. And then there are node pointer which will contain information about each node, channel will contain information about the channel states, the different states that we talked about. And there are two different statistics records for calculating delay as well as throughput of the given system, okay. So these are the basic definitions in terms of variables in the system, okay. And we will now look at some definitions. So packet generation, similar to the arrival, this is again helper function, right. This will be, this is like an event handler, right. So whenever the packet is generated, this event is going to get called. So this is very similar to what we saw before, it simply calls this function called generate sender, and then it determines the time that the next packet is going to get generated. Again it is based on this exponential distribution. This is not based on process delay, this look at the difference here. There I used a process in the previous example for arrival process. Now I am simulating the arrivals as a set of events. So I start with one event per node, that is the first arrival, and then subsequently it reschedules the same event over and over again, but the time between two events getting rescheduled is simply the inter arrival time, and that in this case is exponentially distributed, right. So that is what we have here. So therefore assume that in the beginning of the system node, I have to do this for every node, right. There are 10 nodes, every node has an independent packet generation process, a packet generation sequence, okay. So therefore we will create initially 10 events if there are 10 nodes, and therefore each event, each node will then have a series of events. Every time this event is triggered, a packet is going to get added to your particular queue. That is what this system is, that is the basic packet generation, okay. Generate packet is where we will, so this is generate packet for a particular sender, okay. So what we do is we need to first to determine the receiver for this particular packet. Remember that this is now communication, right. So every sender has to find or has to tell whether who the intended receiver is, and the intended receiver in a Aloha system it does not matter because it is a broadcast system, but we just do a receiver for a particular reason. This is the Aloha with multiple channels also it supports, right. So we will not worry about that right now. So then we look at this infinite buffers. Infinite buffers is true means I can simply go and insert the packet. So this is a small routine that I have written as part of adding packets to a given queue. So every node has a corresponding packet buffer associated, that is simply a linked list, that is all. I simply keep adding on to that linked list, and then I will insert delete from that queue as and when needed, right. This is how my buffer is now. I explicitly have a buffer for every sender in this particular scenario, okay. So therefore I simply create the packet, figure out who the sender is, and then I update all the information. So the packet length is updated, the packet's arrival time is updated, sender receiver, all of this is stored in the packet, and this is in turn stored in the sender's packet buffer. Does it make sense what we are trying to do here, right. So a packet arrives, I put it in the sender's buffer, ultimately that is what is happening, okay, that is all. So then as and when packets arrive, they keep on getting added to this queue. This is the packet generation process, and this is done for every sender. So there are 10 senders, means there are 10 separate threads which are generating packets, and the packets keep going to that corresponding senders queue. There are 10 sender queues, and every sender queue has its own set of packets generated by that particular node, okay. So that is what we have here, okay. Now the transmit packet, okay. So let us before we come to transmit packet, let us jump to user main, that will tell us the sequence of what is going on. So what is happening in user main? In user main, let us, this is where the system starts, right. So there are 10 nodes, 50 nodes, whatever it is. For every node I create the buffer, and I set the status to be idle initially, and I define some default backup probability. Ignore that for the time being, every node has some backup probability that it keeps updating, right. All we need to know is for every node I started being idle and I create the buffer for that node. Buffer is of course initially empty, and then the channel status is simply set to idle channel initially, and in a given slot I keep track of the number of users who try to use that channel, who try to send on that channel, and that is what this user count variable is going to be used. This is updated every slot, initially it is set to 0, right. That is all. I have created my set of nodes and I have created the channel information, okay. That is the basic thing. Now let us try to look at the set of all these statistics records, we are going to skip for the time being, okay. Now I have to create the first event, right. So now I look at this loop here, I have this loop running for 0 to all the nodes in the system, and for each node I am creating a packet generation event, okay. So this is the event that is created, and then I am asking it to be associated with packet gen. This is the function that we saw before. So every node has an event associated which will simply execute that packet gen, and because there are 10 such nodes or 50 such nodes in the system, I have to somehow encode, right. When an event is triggered, I need to know whether this is a sender for packet or this is the event for packet, or sorry, event for sender number 5 or sender number 10 and things like that. That encoding is done with the help of this set argument, which I am skipping for now. It is very easy to encode that, a given event belongs to sender number 6, sender number 7 and so on. So that is very straightforward, okay. So then again I schedule this event, and remember this is the first time I am scheduling it, and the rescheduling takes place inside packet gen itself, and the rescheduling is done based on the next arrival time for the particular sender. This is the sequence that is going on. So now I have created all the packet generation events for all the nodes in the system, and there is also, so that is the one that adds packets to the queue. I also have to have another process or another event, in this case we are making it a process, right. So for every sender I am also creating a transmit packet process. This is the actual transmission process, okay. So there are the packets coming in from the layer to this queue. I need to have a process that looks at this queue every time unit, processes the packets and then sends it out, right. Therefore I need a process for that. Here I am using a combination of both event as well as process. So the packet transmission process is now equivalent to the server resource that we saw before. Now I am explicitly coding the queuing and dequeuing in this particular case. So there is a transmit process that is associated with every sender, every node in the system, and its job is to take the top of the queue, try to send the packet. If it succeeds, good. If it does not succeed, wait until success, retransmit later on. All these things is done by this transmit packet business, okay. So that is what this is. So now for every process or for every node I create a new process, right, and then I encode the process ID so that we can use it for some point in time, and this is simply scheduled once, okay. That is all. So this will now be actually, if you look at the code for this, will be an endless loop, right. While loop will be there that runs forever, but that is all that we are trying to do. So these are the two main things. In every node I am encoding the addition packet generation process and the packet transmission process. This is all that basic system that we need to do, and I am using this driver auto terminate, right, which is we will not get into that. This will again, if convergence occurs sooner, it will stop the simulation earlier, otherwise it will simply run until max time, and when the simulation finishes at the end of it, I will look at the mean total delay, right, per packet, and the channel throughput is also measured here, and how long the system actually run. This is what at the end of the system, that is all I care about, right. What is the average delay, what is the average throughput, what is the average throughput defined as the number of packets, successful packets transmitted per unit time. That is the definition of throughput in this particular system, okay. So questions. So generation, transmission, and the basic recording, that is all. Now what should be the logic that every node should execute in every slot? What should be the logic? Before we look at the code, let us visualize that logic, right. So the transmit process will look at the queue. If the queue is empty, nothing, that sender has no job to do for that particular slot. If the queue is not empty, it will simply try to send this packet. Okay. Now remember, this is happening in parallel. If there are 5 senders, each sender will at the beginning of that slot try to send their packet at that same point in time. Okay. So somehow I need a mechanism to keep track, and these things will all happen at the same, let us say current simulation time is 15.0, right, beginning of a slot. 15.0, 4 nodes have a packet to send. All of them will execute at that same simulation time in some sequence. It is still a uniprocessor system, right, but in some sequence node 5 will try first, node 10, node 11, node 12, but they are all actually executing at the same simulation time, right. Sequentially it might happen at different points of real time, but simulation time wise they are all happening at the same instant of time. So now what I can do is I can simply update this user count, the number of users accessing the channel, right, I can simply update that. So what happens is it is set to 0 at the beginning of a slot. The first user comes, it will increment that counter to 1. Second user tries in the same slot, right, second user has a packet to send and it tries to transmit, it will increment that counter to 2, 3, 4 and so on. Okay. So collision is defined as, under what condition is there a collision? Whenever the user count is more than 1. When the user count equals to 1, this packet has been successful. Now when will I know that? I will know that as soon as, if say 15.0 I did all this execution, at 15.1 if I look at the simulation, if I look at the system, right, state at 15.1 or 15.2, whatever it is, at some intermediate point I can look at the system state on this channel user count. So I look at that. So every node what it will do is it will first go and update this variable at that 15.0. Then I am arbitrarily defined at 15.5, right, halfway into the slot, these guys will come back and look at that user count. If the user count is greater than 1, it means that somebody else has also attempted, therefore collision has taken place. That is the way I am defining collision and I am detecting collision. That is not how the system actually behaves. System will actually try to listen whether there is a collision, or the receiver will simply have a collision, will not be able to get the packet at all, but we cannot do that in our simulation. So we are trying to emulate what is going on by looking at the number of users that access the channel at a given point in time. Okay. So that is what the logic is all about. So basic logic is t equals whatever, beginning of a slot, attempt to send the packet, halfway into the slot try to find out what the channel count is. If the channel count equals 1, wonderful, packet is successful. If it is greater than 1, packet is not successful, then you will have to retransmit this packet. Alright, that is the basic logic that we will have. Okay, now let us look at this transmit packet business. So it is a little bit more complicated because of all this that is going on. Okay. So first is to decide whether a given node will send in a slot. So when will a node send in a slot? This might be a little bit complicated, but if you dissect this, it won't be that hard, right? If a node is currently in back off state, which means it had a packet to send, but it could not send before, and it is now flipping a coin, right? And let us say this is, and it has a back off probability, right? So if I flip a coin, if a back off probability say 0.1, right, and if I generate a uniform random number between 0 and 1.0, as long as this uniform number is less than 0.1, it means that I am going to attempt transmission. If it is greater than 0.1, I will not attempt transmission. That is again, right, that is the way that you define this emulating a uniform behavior, right. So if I am in back off and if I have decided by this toss of coin to actually resend, then I go to transmit state. Or if I was idle in my previous slot and now there is a packet to send in the queue. This is the two possibilities, right. Either I had no packet in the queue before and now I have a packet, so I have to go to transmit state. Therefore I go to transmit state, that is all. And I look at the first packet in the queue, that is the packet, I just get the first packet in the queue's pointer, right, that is all we do. Packet pointer equals this and node info equals node transmit. And those of you who know assert will know why we are using assert, right. This is your standard C programming practice. I want to make sure that I do not have some mess ups in my packet buffer code. So if it is equal to null, that means something went wrong. Okay. So anyway, I have extracted the pointer to the top packet of the queue and I am setting myself into node transmit state, step 1. Then in case I did not go into node transmit state, the rest of this slot I can simply skip, right. So in case I am going into node transmit state, so what do I do? I simply increment this user count variable by 1. Now here actually I should be using a semaphore for mutual exclusion, I am not using that because I am sure that at a given point in time only one process will be executing this particular, but to be correct I should be using a semaphore there for mutex, okay, that let us for the time being ignore that. And if the user count is set to 1, then because what I do is when I increment I can always check, right, if there is already some other users incremented. Remember that there are 4 users but they are all executing at the same simulation time, right, this is like your. So if I just set these 2 variables, we will use this variable later on, okay. Then once I increment this counter I simply process delay 0.5, now see where process delay is very handy, right. So at 15.0 I checked, I change the variable user count variable at 15 until 15.5 I go to sleep, why, so that other processes can then update this variable based on their logic, right. So if that is why I give the I go to sleep, so that 3 other processes waiting to send a packet who are all also in this no transmit phase state can update this variable. So at the end of 0.5 I know that everybody who has wanted to update that variable has had a chance to update, there is nothing else that can happen in the system, alright. So then I wake up and I examine the channel status, if the channel status means only one user was there, right, excellent, then you reset it to 0 because next slot I have to make sure that it is 0, right. Then after this what is there, some other things that I set the channel status to idle and so on, but basically I have to again delay this particular process, whichever process was successful I delayed for another half a unit of time, why, that is to finish the slot, right. At 15.0 I try to send, 15.5 I check the status said I am the only user, therefore my packet is successful, so I have to then wait until this entire slot is finished before I can do all the packet success processing, right. What does packet success processing involve, removing this packet from the queue, updating the delay variables, right, all those things, all the statistics has to be gathered. So I simply again, if I am the only user, right, if it is channel 1 user I then process delay for 0.5 and then I process the packet success at that point in time for this particular process. Otherwise what do we do, nothing else to be done, you simply set the, if there are more than 1 users therefore collision has taken place, you simply delay for another 0.5 units of time and then nothing else for this process, that is why you change the state correspondingly, right, you would be in node back off state, right, you went to transmit state, you go back to back off saying oh previous slot was a collision, nothing much can be done about that, therefore I go into collision state, that is all, right. So from node idle you would have gone to node transmit, from node transmit you will go to node back off, then at some point in time when you decide to retransmit you will go from node back off to node transmit, if that is successful you go back to node idle, if that is not successful then you keep on being in node back off for some long period of time, that is what the node goes through, okay. So this is what you have done, right, every slot you have checked whether the slot is collision or not collision, whenever there is collision I have to invoke this packet success, right, this is what we try to do. This most okay. So packet success, now what is packet success going to do, packet success will handle all the successful transmission, right, components of it. Now remember that there is a big if else statement, if I am not transmitting in a particular slot then what do, I simply have to sleep this entire slot, so I have this process delay 1.0 saying nothing much to do in this slot, bye bye, I will wake up in the next slot. So therefore this transmit process for every node will keep on waking up every 1 unit of time and then process it. Now this is actually what happens is this looks very nice, but when you look at it in simulation, if I put 1000 users, right, there are 1000 users doing this checking, okay, there are 1000 processes running, so it is not a very efficient way of processing, but this is a very natural way of processing. I simply think about one process for every user and I can codify whatever I want to. I could have replaced this multiple process with a single process also, right, because I have global variables anyway. I could have simply looked at the status of all the users, okay, all these guys have packet to send, therefore no point, there is a collision. I can simplify this implementation if I want to, but I have just used a little bit right easy to understand implementation, because we have to think of the node from a system from the system perspective. How does the system behave, you want to emulate that, and then you can do optimization saying wait a minute, this is too complicated, right, because of if you run this for many, if you for example things like OpNet and so on, it takes such a long time because there are like gazillion events getting handled there, and you have no way of changing those things. You cannot say, well, let me simplify the way that events are being generated and therefore I can cut it down. You cannot really do that. With the axiom you can do that, because you are the one creating pretty much every event that you want. Okay, so that's what we have then. So then the successful event is updating the total delay. So you look at the current time minus when the packet started, that is the time taken for the packet delay, right? That's how long it took to service this packet, because this involves all the retransmissions and everything and so on. And every time a packet is successfully sent, you simply update the throughput. One packet has been sent, that's all. That's what this 1.0 represents. Delete the packet from the corresponding sender, and that's pretty much all that is, and freeing all that, right? So that is what is the basic logic of the system. So even a simple system like Aloha requires fair amount of thinking to get the logic right, and this also took me several rounds of getting this logic right. Okay, the way I did the backup probabilities was not correct when I did the implementation, and I compared this simulation to theoretical results. My results were not coming correctly, and I couldn't figure out why, because I told this in class earlier on, right? The way I did the backup implementation did not match what I was using in theory. I was using a uniform random variable there. Here I am using a geometric random variable, and that will make a difference to your delay values. So that those things were also cropping up. So you have to make sure that what you are implementing in as a mathematical model matches reasonably close to what you are trying to do here. Okay, so that is the code part, and the rest of it is all straightforward. You have seen this, right? So the logic clear. Questions?
Uniform function is written by ourselves?
The uniform function is part of Axiom. Axiom has a few default functions. The source code I don't have here. If you look at the source code, you will look at all those functions. You can go and add your own variables also if you want. It's fairly straightforward to add. Other things that would be similar to this is people have used, I think, SimJava, which I have not used. If you are a Java expert, people are also familiar with Python now. So there is SimPy, which I have not tried. So you can look at SimPy, which again, you basically, depending on what you want to implement, you choose a simulator, whether just a bare bones discrete event simulation that gives you only events and processes handling, that's all, or if you want something that has all the protocols implemented, then you go for OMNet++ and all the packages that come with it, or OpNet and all the packages that come with it, right? But anytime you go for a large package scenario, you have to realize that many errors you may not be able to understand where they happen, why they happen. It takes time to figure out changes, whereas there is much more control over the code definition here. Okay, so if there are no questions on the logic part, then let us try to run this. Okay, so those are the number of nodes. So let us say 10 nodes. Okay, and arrival rate, what should the arrival rate be? For a single channel Aloha, what should be the maximum arrival rate before system starts collapsing? Started Aloha. The total offered load should be less than 1. Right? If the total offered load goes more than 1, then you will find that the system throughput starts declining. So let us look at say 0.01, right? This is the arrival rate per node, and we will use infinite buffers. Sorry, yeah, I think now that's just finite buffers. Max time, I will say it is 10,000 or 100,000 units of time. Okay, so this is 10 users, each generating 0.01 packets per second. Okay, now what should be the throughput of the system? Expected throughput. Is this a lightly loaded scenario or heavily loaded scenario? It is lightly loaded, and the expected throughput is simply number of users into number of packets generated per unit time. So therefore it should be about 0.1, right? That should be our expected throughput. Let us see if we get that. So here is the output. Number of nodes is 10. This is the rate per user. The delay is 4.42 seconds, and the throughput is 0.0998. Is that close to 0.1? It is kind of close to 0.1. The only thing is this delay one has to verify. How do you verify 4.42 is correct? We do not know. That's when we use that semi-Markov model that I talked about in class. I can use the semi-Markov model to actually verify that the delay values are more or less matching, at least 5%, 10% close to these theoretical values. So it seems to give me reasonable results for this thing. Now if I increase this rate to 0.1, right, what will be the system throughput now? What is the offered load? Offered load is 1, right? Offered load is 1 packet per second. We know from theory that if I offer 1 packet per second, I will only get about 36% theoretically, assuming that it is all Poisson and things like that. So therefore the theoretical maximum throughput of started Aloha is about 36%. but we will see that it's little bit more than that, about 0.4 or so, right. 0.44 is what is the throughput of this particular system. Again, right, number of users 10, load per user is 0.1, delay is now very high, right, delay is now 146. Why? Because lot of packets, lot of retransmissions, right. I have not measured, I can measure in my simulation, right, how many retransmissions were there. I can simply measure the number of retransmissions. Whenever there is a collision, I can keep track of those things. I have not done that. You can very easily manipulate the code to give those statistics also. You can have more detailed diagnostics, right, because how many times was the packet retransmitted, there is nothing that tells us here, but that you can measure in the simulation if you want to. So throughput is 0.44. Okay, it does not match my system, but look at, I got about 14,000 samples, 14,000 samples, right. I am saying that, and this is based on that auto termination. Whenever there is convergence and delay, system will simply stop. So even though I set my upper limit of time to 100,000, system actually finished in 52,000 units, because it felt that delay values had converged, enough samples were there, delay is converging, there is no point in running the simulation any longer. This is automatically done by the Diaxam extension that is there. Okay. So then we have, so now I am going to make this 1. So every node generating every packet every second. So what will happen? What should be the system throughput now? Will be very large or very small? Very small, right. So if the theory tells us that it almost goes to 0. So let us hope that simulation also tells us the same. It did not. It's still reasonably, it's still managing, right. So even though the offered load is 10, somehow the system is still giving us, let us try this with 100 nodes then, right. Somewhere I want to make sure that the system load goes to 0. 100 nodes each generating 1 packet per second should cause a lot of collisions. Now see, now it is taking a long time, because there are 100 processes running, right, and 100 events sequence. So I finally finished. So now you see it is 0.0312. So delay is, now the throughput is very small. I offered 100 packets and only 0.035 packets per second went through. So system throughput is almost close to 0, and delay is of course very high. But look at the number of samples collected, with only 1749. It is saying that no, this is probably only the last data set. Okay. We can actually output the total number of packets transmitted very easily if you wanted to, that we can modify. Okay. So this is in line with expectations. Okay, we know system throughput is low. Is it going to be this low? We don't know. We know it is low. There is some lot of behavior. Why should it be 24,000? We do not really know. That we can only verify with the help of some mathematical model, right? The other model to actually make sure that this is indeed correct. So that is the Aloha model that we wanted to talk about. Okay. So any questions on this? So if you want to make changes to the code, you can change the backoff probability model, right. That is something very easy to change. That you can go in, and I had some sophisticated backoff probability, you can use some other simpler backoff model. You can use I have a adaptive backoff probability in there. You can make it a fixed backoff probability, and then you can look at the performance of the system. In fact, if you remember that ISA model, that semi-Markov model, there the backoff probability is fixed, it is not dynamic, whereas in my case it is dynamic. So dynamic backoff probability can also cause the slightly higher throughput values, because what happens is a lot of collisions you back off to a very small backoff probability, and as the number of collisions decreases, you start climbing up to a higher retransmission probability. That retransmission probability has a big impact on the system performance. And you can now change this Aloha for doing all sorts of P persistent Aloha is there, right. Instead of sending a packet right away the first time, you have probability of Pi, where you decide with probability Pi I will send the packet as soon as it arrives. You can get better performance with PI persistent Aloha and things like that.